Digital Imaging Part 1. The advantages of digital radiography include the workflow. So compared to film screen radiography, there's a huge change in the workflow. We have less people that have to be employed in radiology now, and the workflow is much faster and much more efficient. Image quality, we have quality images, even though we make mistakes, and so that's the image quality. We've got our computer is going to adjust for the brightness, it's going to adjust for the contrast, and so we really have a good quality images. Image processing, we have pre-processing and post-processing, which we'll get into talking about both of those. And so those are major advantages. And finally, the exposure latitude, we have a lot more wiggle room or ability to make a mistake in technique, and that's an advantage in one regard, but it's also a disadvantage in another, in that we can get dose creep from exposure latitude. The final thing is that our repeat rates on positioning have increased since film screen radiography. With film screen radiography, we were so concerned about technique and trying to be precise that in our images, we had to have perfect positioning. So positioning has become lax over time, and so it's a disadvantage. Exposure latitude. The more vertical line, looking at these two curves, is the one that's A, and that's more vertical, so it has a higher contrast. B has a lower contrast, it's more horizontal. And so the lower the contrast, which is B, the wider the exposure latitude. Exposure latitude is the range of exposures at which produces quality images at appropriate patient dose. It's the margin of error that you can make a wiggle room in setting a technique. And the longer the scale, the lower the contrast, the wider the exposure latitude. Just to repeat that again. So letter B would be the one with the longer scale with the lower contrast with the wider exposure latitude. Film screen radiography is looking at the blue curve, and only exposures within the slope of the curve display acceptable density and contrast. So there's a very small range that was acceptable. Digital radiography has a linear response, similar image quality, whether the exposure is high or low. So there's a lot more exposure latitude with digital detectors. And so exposure latitude, the raw image data itself is a line. It has a wide exposure latitude, and the image itself comes out with a very low contrast if you're taking a look at the image. On the right-hand side, when the lookup table is applied, it actually looks more like that film screen curve that we looked at just a few minutes ago. And the CR imaging system, now that they're showing here, is now a really good quality image. So the raw image data looks pretty rough over here on the left, but the lookup table is applied and it fixes the image. So wide exposure latitude provides acceptable images even when significant overexposure has occurred. And that's the bad part about dose creep. So underexposure latitude, we don't really have a whole lot of wiggle room with underexposure. We only have 25%. But as far as overexposure, 400 to 800%, you could overexpose your patient by that amount and still have a good quality image. So as I've already said, the result of exposure latitude in digital radiography is dose creep. SNR stands for signal to noise ratio. The signal are the transmitted X-rays. The noise is useless information. So a high SNR, which is what we would want, has a high number of X-rays with low noise because we would have low noise. We would want this. Low SNR is low number of X-rays with high noise. So with severely low SNR, we have photon starvation with empty pixels. And on the left-hand side, we can see this image, which has that grainy appearance, and that's referred to as we know as quantum noise, otherwise called quantum model. Severely high SNR can result in, first of all, one thing called plate saturation. And with plate saturation, we get what is referred to as low contrast. So looking at this area, there's and we blow it up, we've lost the long markings and we have very low contrast. So plate saturation with low contrast, and then data drop is the other option that we could have. So this area here in the ilium, we're missing part of the ilium, so it's called data drop. So detectors is what we're concerned about. We have the X-ray tube. We're going to go down here to our digital detector, which is going to collect our X-rays, and it's going to eventually get to an electronic signal, otherwise called analog signal. And so we're going to focus on the digital detector right now. The first digital detector is computed radiography, where we have an X-ray tube, and the detector in this case is going to be a CR detector, otherwise called an imaging plate inside of there. We're going to scan the imaging plate with the laser beam, which is red. We're going to collect the light, which is PSL. It's going to go off to a digital processor, which is going to digitize and quantize the image. And then it's going to process it for the actual image display. We're going to erase the imaging plate, which is going to be part of the process, and then the imaging plate's ready for another exposure. So we're going to take a look at this process. So starting off with, we have the digital detector used in CR as an imaging plate with a PSP inside of it. So imaging plates have a barcode for easy identification. It has a protective cassette, usually made of aluminum or aluminum honeycomb panel, and the front is aluminum and the back is lined with lead. So we have these different layers which are important to us. The phosphor layer is the most important part because it's where we have the PSP. But we have a protective layer above it. We've got a conductor layer, a support layer, a light shield layer, and a backing layer made of lead. PSPs in our active layer. So let's take a look at the two different types. We have a turbid PSP, which is a conventional powder. It's randomly dispositioned throughout the binder. It appears white due to the small PSP particles, which are 3 to 10 micrometers that scatter light excessively. They're mechanically stable, electrostatically protected, and fashioned to optimize the intensity of stimulated light. The type of material that's used in the PSPs is europium activated barium fluorohalide, and the halide can be bromine or iodide. But notice it has europium as the key thing here. That's an important factor in the PSP. It has to be a europium activated. Next, we have the needle PSP, which is down here in the bottom, and it has phosphorus grown as linear filaments. They enhance absorption of X-rays and limit the spread of stimulated emission. The types of materials are cesium iodide with europium, again, is europium activated, and cesium bromide, which is europium activated as well. The plate reader, also called a CR reader or image reader device, is going to scan the exposed imaging plate. It will render the latent image visible. Oops, I misspelled visible. The preliminary steps for CR are image acquisition, image plate scanning, and imaging plate erasure. So imaging acquisition. So X-rays strike the PSP, which really is exit radiation from the patient. It's absorbed in the PSP, and the photoelectrons excite the low-energy electrons to create the holes in the phosphor. About half of the electron holes will recompose and emit light photons. Fluorohalides will hold or trap the other half of the electrons, creating holes at the europium sites. And those europium electron holes are the actual latent image. Then we're going to process the latent image by loading the cassette into the CR reader. When the cassette opens, the imaging plate comes out and we have a red laser beam that's going to scan the imaging plate to free the trapped electrons. Then we're going to have a PSL, which is the photostimulable luminescence or light, which is the blue-violet color, and it's emitted when electrons move from a higher to a lower energy state. Now for a point scan reader to collect data, we're going to have the movement of the imaging plate is going to be slow. Movement across the imaging plate, meaning that the raster pattern going from left to right at the top of the page is going to be fast. And the laser beam is going to stimulate trapped electrons, resulting in the remission of the PSL. A photomultiplier tube is going to convert the PSL into an electronic signal, and the ADC converts the analog to digital signal. So taking a look at this, that green part is going to be the imaging plate. It's going to move slowly through the imaging system. We're going to have a fast raster pattern fast scan raster pattern, which is going to move the red laser light across the imaging plate. We're going to have the PSL come off of there. It's going to be a blue violet light. It's going to be collected by the photomultiplier tube, which is going to convert it to an electronic signal, and then it's going to go off to the ADC. On a line scan reader, the plate remains stationary, and that red laser is going to scan an entire line at one time instead of just at a point. And so PSL is still going to be that blue violet light is going to be emitted, collected by the optical system, and then sent to the photodetector, which is the CCD. That CCD will convert that PSL to an electronic signal, and the ADC converts analog to digital. And here's a picture of the stationary imaging plate, the entire line scan reader, where the laser comes down and strikes the entire line on the plate. And we're going to have the PSL that's going to be emitted and coming up to the CCD, where it's going to be converted to an electronic signal. And finally, we have an imaging plate erasure. The residual latent image is erased by exposure to intense white light, and the erased imaging plate can be reused. So in our step-by-step process, we have the X-ray tube, we have the patient, and our X-ray radiation is going to strike that imaging plate. Our red laser is going to strike the imaging plate when we get it into the scanner. It's going to emit the PSL, which is going to be a blue-violet color. It's going to go off to be red and go off to the computer for processing. In the meantime, the imaging plate is going to go through plate erasure, which is a white light. Sampling frequency. This is the laser beam that scans each line of the imaging plate that correlates to one line spacing or pixel pitch. Now, pixel pitch is also called sampling pitch. It's going to be known as the center of one pixel to the center of the next adjacent pixel. And the smaller the pixel pitch, the higher the spatial resolution. The distance between adjacent pixels is known as, for CR, is known as sampling frequency. And pixel pitch is going to determine the maximum spatial resolution. This is also known as the Nyquist frequency. Sampling frequency is also known as the frequency at which samples acquired from the detector, and it's measured in pixels per millimeter. So now let's talk about digital radiography, or DR. In this case, we're going to talk about scintillators first, then we'll talk about the different detectors. So scintillators are only used in indirect capture. The only time we have indirect capture is when we have X-rays converted to light. When you use a turbid scintillator, we're using gadolinium oxysulfide. It's going to spread light in all directions, just like the turbid PSP did. The needle scintillator, which is going to convert X-rays to light as well, it's grown as linear filaments, just like the PSP was. But in this case, we're going to absorb light, just like we did with that too, and it's going to be a lot better scintillator. We'll use cesium iodide. So the indirect CCD detector, we first of all have our scintillator, which is the cesium iodide. They call it a phosphor because phosphors emit light too. Then we have the fiber optics, which is the fiber optic tape that they're showing. And then the CCD down below. So the CCD is going to convert light to an electronic signal. And then we have the ADC. In the indirect CMOS detector, which is used in dental hygiene, we're going to use a scintillator again, which is cesium iodide. We've got the fiber optics again, and then we have CMOS. And CMOS is going to convert that light to an electronic signal. So indirect capture, which involves the use of a scintillator always, has cesium iodide or gadolinium oxysulfide and amorphous silicon for its photodiode. Silicon, its second letter is an I, just like indirect capture starts with an I. Direct capture has no scintillator and it has a photoconductor, which is amorphous selenium. Both of them are going to look the same as far as the cassettes, or if they're cassetteless. So here's the cassette base and here's the cassette list, just looking at two different types of flat panel detectors. In the indirect flat panel detector process, we have the scintillator converts X-rays to light. The light strikes amorphous silicon, which is a photodiode, and is converted to an electronic signal. Charges are collected at the TFT and stored as a latent image. They're read right line by line to the computer for processing, and we go to the ADC. So you can see here in this picture, we've got the X-rays going to hit the scintillator, and it's going to convert X-rays to light. And then the amorphous silicon is the array down here, is where it's going to change to an electronic signal. In the direct flat panel detector, we have X-rays coming down and they're going directly to amorphous selenium. And then we're going to get an electronic signal going on. So X-rays strike amorphous selenium, converted to an electronic signal. Charges are collected at the TFT, stored as a latent image, read out line by line to the computer for processing, and goes to the ADC. In this picture, I like that they showed the TFT and the storage capacitor down here as well. So the indirect versus direct process, the indirect capture has lower spatial resolution due to the spreading of light and the scintillation of layer. So we're going to have spreading of light, we're going to have less spatial resolution. Indirect capture results in lower patient dose because we have light. If we have light, we have a higher DQE. So that's detective quantum efficiency. So the electronic signal, there's a lot more electronic signal than there was X-rays to start with. And the direct capture has a higher spatial resolution because there is no light. And the direct capture does unfortunately result in higher patient dose. So each DEL has a sensing area, which is that green area called a pixel detector, sensing area fill factor. It's going to be the amorphous selenium or amorphous silicon. It has a capacitor, which is used for storage of electrons. And then finally has a TFT, which is known as the switch. It turns it off and on, used for electronic readout. And the DELs are referred to as pixels. The fill factor is approximately 80%, so that means that 20% of your beam does not contribute to your image. And so this is just a pixel, looking at an array of pixels in a flat panel detector, and we're looking at each individual DEL, and they're just showing you what it looks like. So you've got the storage capacitor, the TFT, and then the capture element, which is in green here. And so DELs, something else, or other components are switching electronics to activate each row of pixels and electronic amplifiers. And so they're going to have associated electronic devices for signal readout from each column of pixels. So here's the amplifiers and the multiplexer and that kind of thing. So there's going to be a matrix readout. The pixels are read pixel by pixel and column by column. We're eventually going to get that process to go to the ADC and then off to the computer for processing. When we're looking at this picture, we're looking at the difference between indirect and direct detectors. The indirect is going to have, as stated before, it's going to have the X-ray scintillator. So changing X-rays to light, that's the first thing we do when we have indirect capture. On the direct detector, they're going to go directly to the X-ray photoconductor, which is amorphous selenium instead. Now, if you look at the two detectors that are flat panel detectors, they both have TFTs. That's one thing they have in common. So they're going to have the DELs, in other words. In all three cases, we have ADCs, as it's going to go off to the ADC to send the signal to the computer. DQE is called detective quantum efficiency. So it's a measure of the accuracy by which the image receptor converts incoming X-ray signals to the image signal. So the higher DQE, we have a result is our less X-rays and lower patient dose. So the higher the DQE, the less X-rays used to start with, and we have more electronic signal coming out. So this is showing the SNR, which is signal to noise ratio, coming into the detector. There's always system noise that we can't help with, and then there's the signal coming out. And the more signal coming out, the higher the DQE. We're going to talk about this during class, how we compare the three of these. Modulation transfer function. This is the ability of an imaging system to render anatomic objects of different sizes onto an image. It's the ratio of image to object. We're looking at ideally it would be great to have an MTF of 1 because the image size would be the same as the object size. The modulation transfer function is just looking at that, the objects of different sizes. And this concludes our video lesson on part 1 of digital imaging.